Hey guys, welcome back. As I'm sure you guys have read the title, let me just show you what's inside this Amazon package with my rusty knife I forgot outside. Uh-oh. Oh, they're the same boxes. Wow. So I wanted one of these and one of these, and I sort of thought that they had sent me two of the same. Interesting. Well, I guess let's see what's inside, shall we? So, okay, this should be the little one. So let's see what's inside the little one. A user's manual. Here is the current clamp itself. Very nice. Okay, it needs a battery. We'll check what kind of battery it needs after. This must be the zeroing function here, this little button. And 1 millivolts for 100 milliamps and 1 millivolt for 10 milliamps, and off. It's very nice. I wonder if they're supposed to be wrapped around like that. I'm kind of worried about these things coming from, you know, used returns or stuff. I did buy these on Amazon. Again, this video is not sponsored, by the way. If I've actually reached out to Hantek for a sponsorship, and they haven't even emailed me back, so there's that. And this guy, so this is the CC-65, and this should be the CC-650. It is, quite a bit chunkier. Certification, yeah, well, I don't really know how much that really means. An operator's manual. And yeah, another battery required here. Usually they're 9-volt batteries that these things have, but not 100% sure if that'll be that. So yeah, I guess we'll check what kind of batteries that go in here, and then we're gonna scour the house for some batteries, put them each through a couple of tests. This is more of a first look rather than a review. I need to play with some stuff a little bit more than just once to do a review. Yeah, 9-volt battery there. And nine-volt battery there. Okay, so I'm going to chase down two 9-volt batteries, and then we're going to hook these up to the oscilloscope and see what they're all about. So, be right back. Well, I've only managed to find one 9-volt battery because I absolutely hate 9-volt batteries. They drain so quickly. They're only mildly useful. I hate them. Anyway, and they're kind of pricey too. So anyways, I found one, so we can test one of the current clamps at a time. So let's go ahead, and I have a test set up here. I have this current limited to 1 amp. And in fact, if you check the voltage, it's at 12 volts, but it doesn't matter because you hit OK. It's going through a 1 ohm 5 watt resistor, and so there's 0.997 amps, and it's actually at a voltage of 1.45. This is only mildly accurate on here, so I will take probably this measurement as close to gospel. Also, we can check using this Unity UT210E. It's a phenomenal amp clamp, current clamp, and we can check just about. Oh, why is this AC? DC. Oh, I meant to zero and I hit AC. Okay, so 0.955 amps, and if I go here, 0.997, so it's somewhere in that area. There. Yeah. So I'm going to bring in the oscilloscope right here, and you'll see here that we have 20 millivolts per division, because we're going to be starting in the 1 millivolt for 10 milliamp range. I've got the trigger set here. I actually have 20 milliseconds per division in the horizontal. That's just so we get a better idea of the changing current. So I'll turn this on, bring it over here. Also, the wire is very short for this. It's probably about 2 feet. So it's a little short. So now it's on. You see we have a crazy offset going on here. It just dropped down into the negative. So negative roughly 20 millivolts. So I'll hit the zeroing. It seems to take a couple tries. There we go. Just pushed it. And you see now we're pretty much at the 0 volts here. So I'm going to turn this off. I'm going to clamp this onto this wire. Okay, and so far, again, we have a little bit of a negative offset, and I think it's because I'm getting a little bit of noise from the AC hum in the room, but that's fine. Let's give it a shot. I'm going to hit OK here. Alright, so how many millivolts do we have here? Well, let's see. We have 20, so 2, 4, 6, 8, 10, about 200 millivolts. 200 millivolts times 10 for the milliamps, that's roughly 1 amp. This is working. As you can see, the line is a little fuzzy here. That's because it is super sensitive, and so if you speed up the time base here, you'll see that it does average out. It does average out to that 1 amp. So this is working pretty well. And in fact, if we want to check what the actual measurement is here, we can actually go and turn on our cursors and get the vertical cursor. Go right about in the middle, roughly in the middle there, and we'll see here our yeah, just about 100 millivolts. So that's pretty good. We have 100 millivolts, so that's about an amp of output. Actually, it's almost exactly an amp of output, so that works really well. We can turn off our cursors, bring it back to its regular mode. There we go. So that works really well. Let's see if now we can turn this off and do something a little bit more challenging. And I want to show you what the point of a current clamp is, instead of just using a multimeter. And this resistor is kind of warm, which is doing 1 amp at 1.4 volts, so about 1.4 watts. Still well within its spec. So here we have a motor. Now these are going to be a lot harder to check because they move. They have they make changing magnetic fields, which is very disturbing for the Hall effect sensor inside this current clamp, but we're going to test it anyway. This guy at 12 volts will not pull an amp. Certainly it won't. Let's just clamp this. Okay, I'm going to hit the zeroing. Seems like just a quick shot is better than the push and hold. And let's wind this down to about 1 millisecond per division, and I'm going to hit OK. Now I don't think, whoops, I don't think this is going to be a big difference here, because it's going to be a very little current change. Let me press OK. Oh, and we're in reverse. I'm just going to clamp it the other way, flip it around. Okay, so you see here, we do have a signal, but why is it going like this? Why is it doing these kind of jumps? Well, if I just change the volts per division, this is what our current looks like. Well, you might be wondering, how come our current looks like these jumps, these waves? Well, I'll tell you, these waves are actually the windings of the motor, the actual windings distributed by the commutator, activating and deactivating. So when the brush goes over a section, you get a spike of current. Let me just trigger on that. So current will ramp up because now we're on a new winding and we're accelerating the motor. And then when it's in between the windings, you get this ramp down. So the motor is still spinning, it creates a counter EMF, and actually you'll see a ramp down in current. It draws far less current. And then back up, and then back down, and back up. So you can actually see if you've got a bad winding, let's say if it's a shorted winding, it would go spike way up here. An upward spike would mean it's pulling a lot of current, which means that winding is shorted. This thing is actually amazing to see. And yeah, actually you see, I just noticed we're actually going in the negative here. And yeah, so that's actually the motor's counter EMF. That's what slows down an electric motor. But let's see if I put a load on this motor by applying my finger to the gear. See, the current ramps up. So let's see if we can put this in single shot mode. I'm going to move the cursor up here. I'm going to hit single. Alright, it's waiting. Did you see look at these big current spikes here? This is me putting a load on it. I can roll it over this way and this way so we can see. And I can even do it even more obvious than that. If I make this run, I'm going to bring this up here. Let's see if we get a giant current spike. So again, single shot mode. Boom. So look at the current here. This is 20 millivolts per, 5 millivolts per division. So 5, 10, 15, 20. We got about 20 millivolts on this motor that generally pulls about 30 milliamps. So it's actually a 200 milliamp current spike. So that's pretty crazy to see, and you can tell right when that winding stops, when you get off that winding and the motor now is freewheeling at a lower speed. It's pretty interesting. So this is the benefit of using a current clamp on an oscilloscope rather than a multimeter. So that's pretty cool. And I believe we can also average this to figure out the load, the actual current. So let's see if I can center channel 1 like that. I will put a stop. So this is the motor just in idle here, and I'm just gonna turn off the motor so we don't get the sound. I'm gonna hit the cursors, and I'm just going to put the cursors in auto mode. Okay. Actually, it only gave me the horizontal, so let's change that back to manual. And the horizontal cursors, cursor A, gonna move down to, well, let's grab a more of an averagey there. Cursor B, move that guy up about there. And so we are getting roughly 8 millivolts kind of peak to peak without dealing with the noise up here. So we're getting about 8 millivolts peak to peak, which means about 80 milliamps in total draw, sorta. It's not average to that, but you can actually set. You actually have some measurements here, so we could actually measure it. But yeah, this thing is relatively accurate for these low loads and medium loads as well, as you saw with the 1 amp load. I could try this on a bigger load, so let me see if I can set that up and I will bring you back. Okay, so I have a completely jank setup here. So I have chained 4 1 ohm 5 watt resistors in series, giving us 4 ohms of total series resistance. I have a car battery here with 12-ish volts. So it's 12. It's fully charged, maybe 12.8 or something right now. I have the scope set to 10 millivolts per division. I have the current clamp set to 1 millivolt equals 100 milliamps. So if I divide the 12-ish volts by the 4-ish ohms, I'm going to get 3 amps of current. I don't have a fuse on this. I really should. My setup is jank. I've just got wires spun around here. So I see that over here we've got the lead, or the clamp, zeroed, and I'm not going to be able to hold this for long, because if you multiply the 12.6 volts of the battery by 3, you'll get 36-ish watts. But if you add up all the wattage of the resistors, I only have 20 watts. So these are going to get hot. So we're hoping to get the bar up here to the 3rd division point, and that'll give us our 3 amps. So here it goes. And yeah, there it is. So it's just above the 300 millivolts. I can go ahead and I'll stop this, and I'm going to unplug this battery. I'm going to check the resistors. Oh yeah, oh, they're toasty. Okay, so let me just go into the cursors here, and I'm going to put the cursors to manual, and we'll be able to take a measurement. So cursor A, I'll put it right in the middle between the two there, as centered as I can, so it'll give us the average reading without the all the noise. And then I'll switch down to cursor B, and cursor B, I'll bring it right down to our 0 point. There we go. And what do we have here? We have 30.8 millivolts. Each millivolt represents 100 milliamps. Is that right? Yeah, 100 milliamps. So 30 times 100, that gives us 3,000, or let's say 3,080 millivolts. Or sorry, 3,080 millivolts, milliamps. Yep, that means 3.08 amps. So that is exactly what we were expecting to see. Mind my shitty off-the-cuff math. So next thing to do now is to take the 9-volt battery from here and put it into the CC-650. We can test it at 3 amps. I'm not sure if I can push it up higher, but I'll see what I can do for you guys. So we've got everything set up just like it was before for the CC-65, but now with the CC-650. We are expecting 3 amps of current, and this is 1 millivolt per 100 milliamps of current. So we're expecting about at 10 millivolts per division, about 30 millivolts, so 3 divisions. It should climb up to here. So let me just turn this on. There we go. And now we see we have a small voltage offset here. I'm going to try to zero that. It has not zeroed. I find these things are a little finicky to zero. I feel like you have to hold the button for a long time. I haven't actually checked the instructions on these clamps yet, but there we go, that looks zeroed there. And don't forget, I am dissipating a lot of heat here, so I won't be able to hold it long. So here goes. Should have about 3 amps, so we should see, yep, up there we have just about 30 millivolts. So that's pretty good. I will disconnect that. We can also try in the 1 millivolt per amp division. or setting, I should say. But in this case, we are expecting that it goes up such a small amount that I'm not quite sure if we'll see it, but we can check nonetheless. And it did. It went up a bit, you know, but at this resolution, there's so much noise on the line here that I don't think I would necessarily trust that. We could try speeding up the scope display and just tracking back and forth, but at that point, kind of what's the point? So now what we could do is we can disconnect two of these resistors, which are quite warm already, and that will give us a 2 ohm load, and we are going to pull 12 volts divided by 2 ohms. We are going to expect a current of roughly 6 amps, and 6 amps is doable, but not for long. These resistors are going to get hot. So I'm going to swap this down to the 1 millivolt for 100 milliamps. We are expecting a 60 millivolts here. So let's just make sure this is zeroed. These things really are finicky to zero out. There we go. Okay, well, I hope everything is recording, because I feel like I can only do this once. And here goes. Oh yeah. Up here, stop. Hopefully I hit stop and not auto. There we go. Alright. Oh no, I missed the waveform. Okay, let's go back. I'm going to do this one more time for science. This down here. Just about here. Like that. Move your trigger up a bit. Like that. You know what? Maybe I will do this. It looks fairly zeroed. So I think I'm going to do this as a single shot. Give that a try. It says it's waiting right now. Let's see. And change the range here. So 20 millivolts per division. So that makes 2, 4, 6, 8. Got 80 millivolts right off the bat here, which means 8 amps, which is possible because these resistors are rapidly changing temperature. We'll see if we can compress this a little bit. Maybe we'll compress it quite a bit and try it again. Put into, try to zero this again. There we go. Single shot mode. Alright, it does say waiting up there. So 3, 2, 1. And let's see, 20 millivolts, so 2, 4, 6. So yeah, 60 millivolts, which means 6 amps. So this is kind of right on the money. Could try again, but this time we'll go into the 1 millivolt per amp, and I'm going to drop this down a little bit. So that's the 5 millivolt range, 5 per division. Zero this out again. Okay, so 1 millivolt for 1 amp. We're expecting 6 millivolts. Actually, we can drop that down a bit too. There we go. 1. So we're expecting 6. So it should climb 1, 2, 3, 4, 5, 6 all the way up here. I'm going to set my trigger level. Come on down over here. And again, we'll do this quickly. Yep, that's exactly what we're getting. So this is reasonably accurate. I do want to test this out on a far bigger load because This is a bit nuts. 6 amps isn't a lot to test on a current clamp that should go up to about 650 amps. But for that, I'll need a slightly different setup, so I'll have to bring you back some other time. But for now, I think the CC-650 and the CC-65 would be an awesome current clamp to add to your repertoire. If you're only doing low current stuff, the CC-65 is plenty fine for you. But if you need the higher current capability, the CC-650 is also a very good option. So I hope you like this first look. This is not a review because I cannot review a product until I have thoroughly tested, or at least somewhat thoroughly tested it. So look for a review in the future, as I'll be playing with this more and more and trying higher current stuff, like putting it on the checking alternator outputs of automotive, cranking voltages, etc. But until then, thanks again for watching, and I will see you next time.